So hi students, today we have to discuss two topics. First one is LC oscillation. The second one is called transformer. Okay, so first let us complete LC oscillation. So before I discuss what is LC oscillation, let me give you the formal definition which you should write in exam. Write down. When a charged capacitor, when a charged capacitor is connected to an inductor in parallel, the charge or current oscillates. Why it oscillates, we will see, don't worry. With a definite frequency. With a definite frequency. F naught equal to 1 by 2 pi root of LC. So this is the frequency with which the charge or the current will oscillate. Provided what you do, you take a charged capacitor, connect it to an inductor in parallel like this. Okay, so this is charge capacitor, this is inductor, connect them like this. Then you will find the charge in the circuit or current in the circuit oscillates from 0 to some maximum value, from maximum value to 0, then from 0 to negative maximum value. Okay, so those oscillations will have a definite frequency given by this formula, which we have seen last class if you remember. Yes or no? This formula you remember? Resonant frequency.
Yes, sir.
These oscillations are called LC oscillations. Okay, so that's it. So first what we will do, mathematically we'll try to understand why oscillations are occurring mathematically. And then I will tell you physically, okay? Tell me what was the equation of SHN? Whenever there is SHN, whenever a physical quantity performs simple harmonic motion, I hope all of you remember, acceleration is minus omega square times displacement. This displacement you can add x also. You remember this one?
Yes, sir.
So I will not again and again derive. How it comes is very simple. In any oscillation, displacement will be a sine omega t. Right? Take one differentiation, you'll get velocity dx by dt. That will give you a omega cos omega t. One more differentiation you do, dv by dt, you will get acceleration. You get minus a omega square sine omega t. Because differentiation of cos is minus sine omega t, and then omega will come. So this is omega square minus a sine omega t is what? X. So I get a equal to minus omega square x. Okay. So we know that if a variable x is oscillating with some angular frequency omega, then this is the relation between acceleration and displacement of that particle. Now, acceleration, how we can write? dv by dt. Agree?
Yes, sir.
And v, how we can write? dx by dt. And this is called double derivative. In mathematics, have you done double derivative?
Yes.
Yes, sir.
Yes.
Now we have to check, no? So this can be written d2x by dt square is equal to minus omega square x. So this is a very nice way of writing simple harmonic motion equation. Usually we write acceleration is equals to minus omega square x. But this is same as this only. Okay, so now understand one thing. Whenever your x will have this kind of equation, it means what? Your x is oscillating. Right? That this x is the displacement of the particle, right? From mean position. So that displacement is oscillating from 0 to amplitude, amplitude to 0, 0 to minus amplitude to 0, right? And the frequency of that is f. And how will you calculate frequency? First find omega, then omega divided by 2 pi. Because omega is 2 pi frequency if you cross multiply. Yes or no? Omega is 2 pi by time period, no? And 1 by time period is frequency. So this is a quick revision of first PU SHM. Okay, now come to this equation. Come to this. I told you if you have a charged capacitor and you connect it to an inductor, this is the situation at time 0. Okay, the charge here is Q naught, let's say, here obviously minus Q naught, and right now current here is 0. Because this is just at the moment when you switched on. This is 0 plus. So just after switching on, charge here is maximum and current here is still 0. The reason why current will not immediately start is this, because this is not resistor. If this was resistor, current will start immediately. But this is inductor, and I hope all of you remember inductor opposes change in current. Yes or no?
Yes.
So inductor's job is to oppose change in current. So inductor will not allow current to change instantly. So if it is 0 now, just 1 nanosecond later also it will be 0. It will take some time, okay, to increase. So this is the situation at time 0. After time t, obviously current will flow, charge will flow from plus to minus, and therefore here the charge will be solve by less now, because if this is plus 10, this is minus 10. If plus 1 will go like this. Students, if this is plus 10 coulomb, minus 10 coulomb, if plus 1 will go like this will become how much? Plus 9.
9.
And this will become minus 9. Agree, na?
Yes.
And that will be in the form of, that will flow here as current here. So please understand, students, this is the situation at time t, sorry. Now, since these two are in parallel, you know that this point and this point should be at same potential. This point and this point should be at same potential. So potential difference here should be same as potential difference here. Potential difference here is Q by C. Everybody agree or not? For voltage.
Yes, sir.
Q equal to CV, Q equal to CV, so V equals to Q by C. So this capacitor you call capacitance, this inductor you will have inductance. Now voltage here is Q by C. Voltage here, if you remember, was minus L di by dt, which is nothing but EMF induced here. Remember or forgot?
Remember, sir. Remember, sir.
You know that those two should be equal because it is in parallel, right? Now Q by C, I let Q by C minus L. This current is instantaneous current. I can write this current as dq by dt. This current can be written dq by dt. Let us write this one first. Where should I write? Here, let me write. So this one will be d2q by dt square. This L you cross multiply, minus 1 by LC. Okay, into Q. Did you see something remarkable? Did you see something very fascinating between this and this?
Charge is oscillating.
Yes, very good. So just like here, X oscillates with frequency omega by 2 pi. Here this equation shows. So first you write till here, then I will write. Equation 1 shows that charge Q in LC circuit oscillates with angular frequency omega given by. Students, if you compare this equation with SHM equation, who is your omega square?
1 by LC.
1 by LC. So omega will be 1 by root LC. And frequency, if you want, will be omega by 2 pi. 1 by 2 pi 1 by root LC. Okay. So if somebody will ask you formula for charge, how will you write? Well, Q naught sine omega t plus phi. This phi is called initial phase. Epoch. It is also called epoch in SHM chapter. But basically, this phi, it tells you what was the value of Q at time 0. For example, at time 0, if somebody will ask what is Q in this formula, what will happen? Q naught sine phi. Yes or no? Check once. If t is 0, what will be Q? Q naught sine phi. Agree or not, students?
Yes.
Yes, sir.
So the value of sine phi will decide what is charge at time 0. So for example, suppose you want phi to be 0. The formula will become Q equal to Q naught sine omega. But if you write this formula, then you are assuming at t0, what is the charge? First you tell, if you take this formula, what is charge at time 0?
0.
Because if you put t0, sine 0 will be 0. Also, you may take phi as 90 degree in this formula. Then Q will be what formula? Q naught cos omega t. Because sine omega t plus 90 degree is cos omega t. If you take this formula, then what are you assuming? At t0, what is Q?
Q naught.
Q naught. So, whether you use sine omega t formula or cos omega t formula, first of all, I hope you understood why I'm using sine and cos, because we know charge is oscillating, right? Now, whether to use sine omega t or cos omega t, that will be decided by the question. So, at time 0, if the charge started with some maximum value, then you should use cos. Because when you put t0, cos 0 will be maximum. So, charge will be maximum. But if you started from the moment when charge is, let's say, 0, then at t0, if you want charge to be 0, you have to write sine omega t. Otherwise, if you are not sure what was the charge at time 0, then you write like this. Understood, students? Everybody?
Yes, sir.
So this is the formula to use when you know at time 0, charge is 0. Similarly, when pendulum is oscillating like this, if you want time 0 to be this position, when pendulum is at mean position, time 0, then you have to use sine omega t. Because at t0, sine 0 will be 0, so displacement will be 0. But if the pendulum is oscillating like this, and when the pendulum is at extreme position here, that time if you want to start your watch, matlab when y is maximum, displacement is maximum, that time you want time to be 0. Then in that case, you have to use cos. If they ask current at any particular time, you can write dq by dt. So the formula for current will depend on formula for charge, whether you have used sine or cos or maybe 60 degree here. I don't know, okay? Can you tell me if this is 60 degree, then what will be charge at time 0? Sine 60 is how much? Root 3 by 2. So the charge will be root 3 by 2 times Q naught at T0 if you took this phi as 60 degree. So basically the value of this phi will decide what was charge at time 0. Okay. Now, physically, let me try to explain. This is not so important for your board exam, but still, it is interesting to know how the charge is oscillating, the cause. So I'll compare the oscillation of charge, the LC circuit with pendulum. Okay. So when you take a charge capacitor plus Q naught minus Q naught, you have already given some charge, and then you have an inductor, and at time 0, you are going to close the Q. This is similar to this state of the pendulum. You have given some maximum displacement, and here what is stored, if you remember, here potential energy is stored right now. Okay. Here electrostatic energy is stored. So let me show this bar as electrostatic energy, UE. And right now there is no current, circuit is open, so the magnetic energy is 0. So magnetic energy is 0. Electrostatic energy right now will be how much? Q naught square by 2C. Yes or no? Half CV square we write, no? But V is nothing but Q by C. So charge stored is Q square by C into half. And since right now the charge is Q naught, the initial charge, I have written Q naught. Now when you close the key, then what happens? Closing the key is similar to leaving the pendulum. Let me repeat one more time. Closing the key here is similar to leaving the pendulum. What that means is, why I'm saying similar is because the moment you close this, the charge will flow from plus to minus. So now here charge will be solpa less. And current here was 0 before. So now current will be, little bit current will flow. Charge has increased or decreased from here to here. Plus 10 minus 10 coulomb. And then I put inductor like this. This plus wants to go to minus, but it is open right now. So when I close it, this plus charges will start going here. Let's assume some current flew, because of which 1 coulomb went like this. When 1 coulomb goes here, this will become how much, Munaza? From 10 coulomb, if 1 coulomb goes like this?
9 coulomb.
And this will become
11. Minus 9.
Increase or decreased?
Decreased.
There is no source only, no battery anywhere. So the charge has to decrease. Clear, no?
Yes, sir.
Any doubt is there means you ask me. What made you feel like it will increase? So, since charge from here to here decreased, it is similar to saying electrostatic energy decreased. Right? It is Q square by 2C now. What about magnetic energy? It will increase. Who remembers the formula for magnetic energy? It is similar to kinetic energy formula last class in Carmel I derived. Pass you tell.
Half L I square.
Half L I. Before there was no I, so there was no magnetic energy, but now there is I, so there is magnetic energy. Can you guess from where this magnetic energy came? Energy cannot be created, no, simply. Who has lost energy to provide this energy?
The capacitor has lost its energy.
Has lost its electrostatic energy. Hey, Nikhil, what rubbish you are writing? Ma? EMFs in inductor means what? So the reason why this has stored energy, now magnetic energy, why it is increased from 0 to this value? From 0 to this, why it increased? Because capacitor's electrostatic energy decreased from here to here. So look here, this is similar to which state of pendulum? When the pendulum is here. At this position, when we started from rest, potential energy was mgh. Let's say this is the height. What was kinetic energy here when it started?
0.
0. So your kinetic energy is like your magnetic energy. And your potential energy, mgh, is like your electrostatic energy. So when you leave it, as it is coming, what is happening? Potential energy is converted to kinetic energy. Correct now? Okay. Now, as this plus 10 coulomb gives 1 coulomb, then 1 coulomb, then 1 coulomb, then 1 coulomb, what happens after some time? A time will come when this will have 0 charge. And that time, current here will be maximum. Okay. So now tell me, what happened to electrostatic energy here? If no charge is 0. And now your magnetic energy is maximum. Half L I naught square. I'm using I naught for maximum current. Okay. This state corresponds to what position here? Now students, at this position, you know there is no driving force. Net force here is 0. Right? Mg will cancel tension. Yes or no, students?
Yes, sir.
So Mg will cancel tension. So net force here is 0. Similarly, Nikhil, what you were saying correctly before, this capacitor was acting like source for this current. That is what mistake you did. You thought it is acting like source for itself. No, it is acting like source for this current. So now you see what happened, Nikhil. Here there is no more charge. So there is no more driving voltage. Just like here, there is no more driving force. There is no more driving voltage. Q V is not there now. So if this body did not have mass, it would have stopped right here. But we all know this body doesn't stop here. Yes or no?
Yes, sir.
Yes, sir.
Yeah.
Continue. Why does it continue? If I ask for one word,
Inertia.
and that inertia is because it has mass. Similarly, this inductor we know has inertia, right? So voltage here has become zero. Remember, driving voltage is zero. Current here is maximum, and that is understandable because voltage in inductor is not I into R, students, not I into R. It is L di by dt. Modulus if you take. And you all know if current is maximum, what is differentiation of maximum?
Zero.
Zero. So that's why there is no voltage right now. Even if voltage is not there, there is still maximum current because this is not resistor. This is inductor. So this driving voltage is not there. Current right now is maximum. So current wants to decrease to zero now because there is no voltage only. But inductor will not allow it to decrease instantly. Just like this mass will continue, this current will continue. So as this current will continue, see next now how it will look. Now this current will go like this, continue, and then it will get stored here. So some plus charge will be stored here. And because now this current is getting stored here as charges, here the current will be less than this maximum. Which means your electrostatic energy has increased slightly from zero, and it is because magnetic energy has decreased. This is similar to what state? The pendulum continued on the other side. Then a time will come when the charge here is maximum and current here that time is zero. This is similar to extreme position. Same as this. So here your electrostatic energy is maximum like at the beginning and magnetic energy is zero. You don't have to write all these, students. Okay, this is just for your clarity. We see mathematically we understood why charge oscillates because the equation of the charge was similar to displacement of SHM. So enough, no, we understood what is there. But this gives you nice clarity of what is happening. Okay. Can you see that this state is similar to this state except one small change? What change can you guess?
The charges on the plate is
The sign of the charges. The sign of the charges is reversed. So now what will happen? This is similar to this. So what happened here? This voltage will drive current. Now this voltage will again drive current. But in what way?
opposite.
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 Plus charges will come this way now. So now this whole cycle will repeat. Okay, so this whole thing will keep repeating with electrostatic energy getting transferred as magnetic energy here. And here magnetic energy getting transferred as electrostatic. And these oscillations will continue forever and ever. But one person is there who will not allow these oscillations to continue forever. Who is that?
Air resistance.
No, that is in pendulum. Electrons, why will they feel air resistance? Which circuit element dissipates?
Resistance. Resistance.
Obviously resistance. So in this circuit, did you see anywhere I made R?
No, sir.
No, sir. That's why these oscillations will continue forever. It's like saying there is a pendulum but no air resistance or no friction in the pivot. So then the oscillation of pendulum will continue forever. So one small note you mentioned. In LC oscillations, if resistance is neglected, then electrostatic energy plus magnetic energy will remain constant. Yes or no? Otherwise, some heat will be dissipated and therefore the oscillations will slowly die. What was electrostatic energy formula? U square by 2C. Magnetic energy half Li square. Also, when this is maximum, this is 0. And when this is maximum, this is 0. In other words, maximum value should match or not. When one is 10, other one is 0. When one is 2, other one is 8. When one is 8, other one is 2. When one is 0, other one should be 10. So maximum value of electrostatic and maximum value of magnetic should match or not? Maximum value of these two should match. What is maximum value of electrostatic energy? Half Q naught square by C. And this is half L I naught square. So this half can be cancelled. So I naught will be, if you cross multiply, 1 by root LC into Q naught, which is omega times Q naught. Okay. Transformer. Can anybody guess what voltage your mobile phone needs? Yeah, around 4 or 5 volts it needs. Okay, Nikhil is writing 5 volt. But how much voltage government gives through power supply? 220 that we have learned in AC.
Yes, sir.
So when you connect mobile to your power supply, your mobile should burn because mobile requires 5 volt. You are giving 220 volt. Similarly, some big appliance like electric heater or geysers, they require 2000 volt like that. But we are giving 220 volt only. So what's going on? So that is where transformer comes into play. Or if you bring a, let's say girls, you will dry your hair, no? What is that called?
Hair dryer. Hair dryer.
Boys will also dry. So that hair dryer, if you bring from US, now in US, the given voltage is not same as India. So if you bring that voltage, that hair dryer from US to India and use for our power supply, either it will not work properly or it will get damaged. So we need something which can increase or decrease the voltage required. And that device which does it, the device which increases or decreases the voltage level, that device is called transformer. And that is where the application of AC comes, because only ACs can be increased in voltage or decreased. Transformer doesn't work for DC. However, there are some other devices where we can actually increase DC voltage also. Okay, but we will not go there right now. So write the definition. It is a device used to increase or decrease AC input voltage using the principle of, what principle it will use? Mutual inductance. So here I have given you definition of transformer also, and also one more definition. They will ask on what principle transformer works, and the answer is it works on the principle of mutual inductance. Faraday's law also we can write, Nikhil, but better to write mutual inductance for board exam. So if it increases the voltage, so if output voltage VO is greater than input voltage VI, then we call it step up transformer. And if your output voltage is less than input voltage, we call it step down transformer. Okay, mention this. We'll see working now. So how does it increase or decrease the voltage? It's quite simple actually. So the way it looks like, the diagram is, it takes a bulk soft iron as a core. What is core? The inside. So it takes a soft iron, a body, a solid soft iron body, and then it laminates. Laminates basically means cutting the bulk conductor into thin sheets. Okay, and then making a hole kind of thing, rectangular hole kind of thing. So if I show you 3D diagram, it will be something like this. So we break the whole conductor into these thin sheets and then we join them. Okay, in the middle we put some insulating material. Why we do all that, you will come to know at the last. But I will not show you the 3D diagram. I will show you from the front. So from the front, you will see only one face. So this will be your laminated core. Laminated soft iron core. Soft iron is used because its permeability is very high. If you remember, relative permeability is very high. It is a ferromagnetic material, and therefore the magnetic field inside will be strong. So it takes a soft iron core like this, and then there are wires which are wound like this. So this part is called your primary coil. Let me use color black only. So this is your primary coil. And here we wind wires with different number of turns. Okay. So this is called your secondary coil. In circuit symbols, they draw like this. So this is your circuit symbol. This represents your input, primary coil. This is your secondary coil, and these lines are there to represent the core. So this is the circuit symbol. Now, listen carefully. Whichever voltage you want to increase or decrease, that AC voltage, you have to connect here. So this is the input voltage VI. Okay, so the applied input voltage is VI. Now students, listen carefully once. As this current changes, because this is alternating voltage, so the current here will alternate. It will go this way and then this way, then this way, then this way. It will create magnetic field around it. Closed magnetic field lines are closed lines. Yes or no? So this magnetic field will also alternate because of this alternating current. Because this magnetic field is produced by this current. So if current alternates, magnetic field also alternates. When magnetic field alternates or changes through this coil, flux in this coil will change. When flux in this coil will change, a voltage will be induced here also. EMF will be induced here also. That EMF induced we are writing now as V naught. To remind you, this is the output voltage. So just let me know this part you guys understood or not. There is mutual inductance here if you see carefully. First of all, there are two coils, and change in current in one coil is inducing not current but voltage. Why no current here right now? Can you guess? Why no current here right now? No circuit. Because it is open circuit right now, right? But voltage can be there, right? Sir, once more, can you explain? Yes, I can explain. So the alternating input voltage will result in alternating current. This changing current will produce changing magnetic flux. So this will produce changing magnetic flux, and this will induce EMF or voltage in the secondary coil. So the alternating input voltage will result in alternating current in primary coil that you mentioned. This alternating current in primary will produce a alternating magnetic field, changing magnetic field, which is a changing magnetic flux. And from Faraday's law or from mutual inductance, we know if magnetic flux changes, EMF is induced in secondary also. Okay, so now let NP and NS be the number of turns in primary and secondary coil. Okay, so NP and NS are what, students? Number of turns in primary and secondary coil. And we assume there is no leakage of magnetic flux. This is an assumption, okay? It's not a very bad assumption because we are using soft iron. Most of the lines will be concentrated in that only. One or two may escape here and there, but that is negligible. So what we are assuming, whatever magnetic flux is produced in the primary, same is also linked with the secondary. So we are assuming let phi be magnetic flux linked with each turn of both primary and secondary. So whatever flux is linked with one turn of primary, same flux is also linked with one turn of secondary. Because if you remember, so this area here and this area here will be same. Yes or no, students? Quickly. Primary, these are turns, no, like this. So if you take one turn here, area will be same. And if I assume same magnetic field is going here also, so B here and B here is also same. So B is same, A is same, B into A, which is magnetic flux through one turn, that also will be same. Clear or not clear? Quickly. Okay. So what I am assuming is the magnetic flux linked with each turn of both the coils are same, and that is phi. Then from Faraday's law, what will be the EMF induced in the secondary? Voltage in the secondary. Well, it is the rate of change of magnetic flux. Yes or no? How much will be the magnetic flux in the secondary? One turn has this much flux. Secondary has how many turns? NS. So NS. NS is constant, take it outside. So this is the flux linked with secondary coil, because secondary coil and primary coil will not have same number of turns. So one turn has same flux, but 10 turns will have 10 into that much. So number of turns in secondary is NS. One turn in secondary has flux 5. So total flux will be NS into 5. NS is constant, take it outside. So this is voltage induced in the secondary. What about voltage induced in primary? Let me write this as output. VO. VI. Or let me write VS only, no problem. But remember, Your Vs is your output voltage, which I wrote before, V naught. And your input voltage is your primary voltage. That will be what? Minus d by dt of magnetic flux in the primary coil. What will be magnetic flux in the primary coil? Number of turns in primary into flux linked with 1 turn. But flux linked with 1 turn is same because I am assuming no leakage of magnetic field. So minus Np d phi by dt. Divide the two equations. First you write this much. If you divide the two equations, you will get the formula between output voltage Vs and input. Now one small thing which many teachers will skip. Let me tell you, all of you. Stop writing. This was the core of the transformer, right? Here was your primary coil. Here was your secondary coil. And here we applied some voltage, input voltage Vi. As current changes, there will be voltage induced here. That voltage induced is this, Vp. Now, why am I assuming input voltage is same as induced voltage? Why? That is only because I am assuming this part has zero resistance, or at least negligible resistance. Otherwise, if some resistance is here, some voltage will go here also, I into R. So applied voltage and induced voltage will not be same. So dividing equation 1 and 2, what will you get? Left hand side, voltage in the secondary divided by voltage in the primary is equals to d phi by dt minus will cancel. Number of turns in secondary by number of turns in primary. So this is a very nice, beautiful relation. So from here we can see case 1. If number of turns in secondary is greater than number of turns in primary, if this is 100, this is 50. 100 divided by 50 will be what? 2. That means voltage in secondary output will be double of input. Matlab your voltage has increased or decreased. So if your number of turns in secondary is greater than number of turns in primary, this voltage is more or this voltage is more, Vs or Vp?
Yes.
Vs.
Yes.
So Vs will be more than Vp. This is your step up transformer. So how to make step up transformer? Just make more turns in the output in the secondary coil. Case 2 will be reverse of this, right? If number of turns in secondary is less than number of turns in primary, then voltage across secondary will be less than across primary input. This is step down transformer. Okay. So now we will relate the current in primary with current in secondary. But for that, you have to put a load. Load matlab some resistance in the secondary coil. You remember, right? Secondary coil was open, no? So here you connect some load, RL. So there will be current in this secondary coil also. Assuming ideal transformer, the input power equals output power, which is never actually true, because there are many losses which occur in transformer. We will study that last topic. 4 losses we need to just mention. So because of those losses, output power in the secondary will be less than in the primary. But if they mention ideal transformer, neglecting all the losses, we can mention this. What is input power? Power is current into voltage. So input power will be current in primary into voltage in primary. Output power, current in secondary, voltage in secondary. So primary current by secondary current will be voltage across secondary by voltage across primary. And you know, this is equal to, this ratio is number of turns in secondary by number of turns in primary. So here it is ulta, you can see. So if you have more turns in secondary, you will have more voltage, but you will get less current. That's why transformer does not violate conservation of energy. So just because it is increasing voltage, I'm not saying it is increasing energy. Voltage it has increased, but at the expense of what? Current. So the product of current and voltage, which is power, power is energy per second. Energy per second you cannot change, students. So if you are increasing voltage in secondary, that is because your current in secondary is less. Okay. What if it is a not ideal transformer? So non-ideal. So for non-ideal transformer, they will mention the efficiency. 30%, 50%, 40%, 0.4, whatever. So efficiency, how will you define? Output power by input power. So efficiency will be I secondary, V secondary divided by input power, which is current into voltage in the primary. So this equation you can use to solve some problems. Okay. So this is all about transformer. Now I will just mention the four losses, then we'll stop. But just write this quickly. By the way, can you guess what is the efficiency of this ideal transformer?
1, sir. 100%.
So remember, in step up transformer, in step up, number of turns in secondary is more, voltage in secondary is more, but current in secondary is less. Okay. Okay, so let us now quickly discuss what are the energy losses. Write down. Energy losses in transformer. So the energy losses in transformer are: number one, magnetic leakage, magnetic flux leakage, or leakage of magnetic flux. So this is one loss, leakage of magnetic flux. Number two, those copper wires which we used, those winding, they themselves will have resistance. I know, I assume their resistance is negligible, but some resistance they will have. And because of that resistance R, there will be some heat loss, I square R. Okay. So that is called your copper wire loss. Okay. Copper wire loss in the windings of the coil. So whether it's primary or secondary, there will be some resistance. So I square R loss. Copper wire loss due to resistance, due to resistance of windings of the coil. Or better to mention, copper wire loss due to resistance of the coil. Third one is your eddy current loss. Already I have discussed eddy current, so I will not discuss now. So basically the current is alternating. So magnetic field is alternating. And whenever you apply changing magnetic flux in a conductor, solid conductor, there will be circulating currents produced. Remember, so those circulating currents are results again in heat. So those currents are eddy current. So that loss is called eddy current loss. That's why lamination is important. So that's the reason why we broke that soft iron into sheets. So that does not allow the current to form closed loop. And the fourth one is your hysteresis loss. Hysteresis loss also I have told in the class. So hysteresis loss matlab what? Again, your magnetic field is alternating. So current is alternating. So if current is like this, magnetic field will be like this. So all the dipoles in that core, the soft iron core, all the dipoles will orient that side when magnetic field is this way. The moment current will change direction, magnetic field will be this way. So now your dipoles will try to turn this way. As current keeps alternating, those dipoles keep fluctuating this way, this way, this way, this way. So this random movement inside the material results again in heat. So that is called hysteresis loss. So these are the 4 losses. How to reduce this one? Use soft iron. Already we have used, right? So soft iron will allow the field lines to be concentrated inside them. So that will reduce this loss. How to reduce this loss? Well, use copper wire because they have the least resistance, right? Eddy current loss, I told you do have to do laminations, okay? Cutting the material into sheets. And how to reduce hysteresis loss? You have to choose a material whose graph of hysteresis is thin. Why thin? Because this area was related to this loss. And if you remember, soft iron had a very thin hysteresis graph. Do you remember? Compared to steel, steel was little fat. Soft iron's hysteresis loop was quite thin. And that's why soft iron is very much useful in transformer. Okay, thank you for today.